got today? So I want to, well, we'll go on with the Frenzo model. We're going to start looking at the next phase of his, get set up for myself here, of his op amps. And unfortunately, I am going to have to, maybe I can come up with a fairly simple comparator type lab for the simulator where you would just have to go through and vary those voltage levels on the op amp device itself instead of being able to play with the values. And what we could try that. I'm working on a couple of them actually right now to go with the simulator limitations, if you will. But yeah, with that in mind, so we look at Frenzel's chapter 36, and you'll see a large part of, at least the beginning part of his chapter, is talking about comparators, going on to something called the integrator and doing waveform conversions. He'll throw different, I don't know, it's kind of a weird chapter the way he jumps around in it, because we also look at throwing in filters. That's another thing that op amps are extremely efficient at and widely used as filters, both low pass and high pass. And how would this differ? So you've done it in AC models, right, where you've done like high pass, low pass, all pass, band pass filtering and everything using RLC circuits, either combinations of, right, resistance, inductance, and capacitance. But those type are what they call passive circuits. So really, you just have components sitting in there, and based on their values, they're sitting idle until they react to signals coming at them. Okay, but when you throw the op amp model in there and make these type of filters, what these kind are active filters. These aren't just sitting and waiting for something to happen. They're making things happen. So he does do a fair job of looking. We'll take a little bit more look at what's involved with harmonics. Yes, I know, and it's a wonderful concept, but and that's what we're going to talk about with first order and second order, and the orders go on. It's like it's almost infinite, right? First order, second order, third order. We could go on to infinity with how many orders are involved in harmonic effects. There really is no limit. The thing to remember when you deal with something like harmonics, what happens is it's wave theory, right? So you have to kind of mentally picture in your head how the wave is occurring. And so we get the pulsing effect, which, and that's the hum you can hear sometimes in electric lines and that type of thing. You can sometimes feel it if you walk in like an electromagnetic field or something like that. But that's the wave that's involved. And you have to think, does the energy just dissipate automatically? So I get this first wave, right? Whoom. Does it dissipate? No. You have reverberations that happen after that. So depending on absorption around the wave, does the wave get fully absorbed? No. So will you get it? A good way to kind of think, and unfortunately, unless going into music and thinking how music works and stuff like that. Well, we get kind of think of it like an echo effect, if you will. So you have the first one, right, and then you get the echo, and the echo comes back, and it's like a reproduction of that signal, but a little less, right? And in a third order, same thing, a little more or less. Fourth order, a little more or less, and on and on and on. Like I say, in infinity, and that's the thing with analog. So. And this actually occurs in a digital world too. They just kind of ignore it, if you will. But and so whenever you deal with sinusoidal signals, that this is what occurs is you literally are having this echo effect continuously and constantly happening. And that's the reason why you get distortion. That's the reason why you get feedback, because they're really, as well as you can, and as much as you try to design these filters to get rid of these signals and reject these signals, if you will, there's never like the perfect. You just kind of basically get to the point where it's good enough. But that's really kind of what we're going to be looking at as far as like when we go and start talking about like first order stages, second order stages, and things like that when we deal with harmonics. But anyway, so comparators. So we use the op amp basically as comparators. And what that means is it's kind of looking at two different signals, if you will. So we have different types. You know, they have the zero reference ones where, well, we'll see the model in a minute. You can use diode clamps to basically, and a diode, as you've seen, it's got the literal 0.7 volt drop across the. So what they'll use like diodes for clamping is basically as protection. It'll keep a large signal from passing through. So if something did come, if it was like a strong enough intensity, you know, it would blow the diode long before it would actually blow the op amp, if you will. But these are like protection circuits that they'll do, and we'll show you a little model here. Now, if you recall from before, we did do this type here, right, where we had the diode clamper. And so if you get a signal going into that, right, it'll diffuse that and kind of reject it in a way if you look down here. And then we start getting back into our wonderful talks of saturation. And yeah, you have saturation effects with op amps because, again, we're still dealing with, ideally, with transistors, right? And at the heart of these things. So we do have cutoff to these guys. We do have saturation. This did not go away with by switching to this. It's just they deal with it a lot better, as basically by our response to the thing. So how is this device? Basically, what happens is what we're running by not having feedback loops in here or anything like that. We're running this thing wide open, open sourced, right? So what becomes our limitations? Well, our limitations are literally, in this case, the VCC and VEE. And that would be like if I pushed a signal large enough to come through, okay, what the limitations would become both the sources right here. And that's what we see by VSAT and the minus VSAT as our output. So our voltage level, let's say like in a simulator ideal model, it's both plus and minus 15. That's what our levels would be. At this point right here, you would have our VSAT would be plus 15 and our minus VSAT would be a minus 15, if you will. So you can do an interesting thing with these guys. So what happens if I drive this bad boy? Now I have what they call like a zero reference, if you will. So now my VCC and VEE have, I could ground the inputs, if you will. And then using these two Zener diodes back to back like this, why would you do something like that, do you suppose? Now, ideally, if you had two Zeners across like this, right, basically they're in a rejection mode. So they try to basically deal with any interference or any noise, if you will. And so what becomes our output at this point is what? If you notice, it's 0.7 and 0.7 in this. And that's because of the driving of the two different diodes tied into the loop like this. So it's a different way of like controlling a comparator, if you will, a rather simple approach. Just if you were going for a specific response for a signal. But they use them for a couple of different things. And one, you could do this with other like transistor devices if you wanted to. But the cool thing about using the op amp for it is it's more reliable. The op amp can handle more without getting shorted out. And then you have a much better, well, but as you've seen with the decibel roll off, we have a much better frequency response with using the op amp versus like if we used a transistor model where we would have a tight bandwidth to it. Here with the op amp, we have a much wider bandwidth ratio, and that's why we would use the op amp for a device like this. So here's a rather simple, and see, and everything with the comparator always ties back to how you control VCC and VEE. And that's why I'm saying, yeah, we're going to chuck lab 10, because with the regulator, with the regulator, with the simulator, I have no way to apply these pins. That's one drawback or inefficiency. Shh. So the best way, I don't know. We can do simple ones like this where we just control the voltage on the op-amp model itself and still look at these. We'll have to kind of consider it as zero reference ones. So I was looking into that. So I'm going to try to get that like 2 labs out if I can, and they're kind of Malvino based. So they should be fairly simple, just to see how it operates, how it functions, why we're doing it, the way we do it. And here we control. Now, compared to the other ones, now why would we call this a non-zero reference? Well, we are literally having nothing tied into this, okay? Whereas here, now we have a little voltage divider circuit providing our voltage reference, if you will, on the one side versus the other side. And so what would happen when you get that signal in there, as you can see, so you get a certain amount of rejection occurring with that, and you're just allowing like really the peak to fall through, if you will, before we get the clipping effect. So yeah, we'll do oh God. So now I have the homework for this guy posted, and yeah, we'll go through the beginning of Frenzel's comparators. I'd also like to talk a little more on comparators with a little bit more reference to it, I guess, if you will. But they do have speed limitations overall. I mean, op-amp in the real world is not ideal. So what we have to do is look at the internal. This would be something that you would pull from the spec sheets of the device, but see what the internal compensation factor is of the op-amp. And overall, and that would dictate like what your RC time constant would be, right? So what's our frequency limitation in a model like this? So really you don't see it going on, but we do have a capacitance effect interfering with that, right? So we would have to take that into account, tie that in, and go, okay, so what does our time constant end up becoming? And it's just an interesting little thing with these guys. But yeah, and this gets into, like I say, our non-linear model, right? So we're not reproducing a nice smooth analog signal. We don't have the feedback loop in this case. So these are all like what they would call open loop functions, if you will. If you look at all the model types, really, this is an open loop. There's no feedback resistors. There's no input resistors to these guys. And this is how the model changes. So as far as that's like linearity as linear response, that kind of goes out the window. And that's a cool thing with comparators. So it does change like how, and again, remember though, I mean, our golden rules of the op-amp of the device itself don't change. It's just the way in which we use them by taking away the feedback loop compared to having a feedback loop, and how the device responds to that. So here's a good little cutaway of what's occurring inside. Now remember, what's going on here on the output, right? If you still think it's that, the Class B amplifier, right? The push-pull. And so that's still occurring internally. And then how that happens, and then what we have as far as how our VCC and VEE are, our bias voltages, how they're going into the device. And this is a nice little cutaway to give you a little idea. So if we look at that as far as our model, we have to think, okay, so we got the one on the one side, right? We have the MPN style transistor, and on the other side we would have the PMP style transistor going on. And that's not to include what's occurring at our inputs here. So really we're looking at how the output is being affected by what we're applying to our VCC and VEE, or our bias voltages, if you will. So, and then we think of that, remember, push-pull is on, off, okay? So when one side is on, the other is off, and when the other side is on, the other is off, and vice versa, always back and forth. So if I have on one side, it's let's say I have VCC hooked up as an on, and then in this case, I put VE to ground like that. So one would be on, off, and then this one would be off, all the time. But when it's in the on phase, I mean, you still have a zero reference, so it would be on, but you just would be getting no output, if you will. Hopefully that makes sense. Oh, here we go. So an interesting thing, and this term should have been something that we got through AC analysis, specifically with inductors, okay? A good way to always look at what is hysteresis. And a way to look at hysteresis is think of it as a delayed response. And a really, really ideal model to look at that is like what happens with magnetism, specifically like with coils, okay? So when we charge the coil up, we do get what? We get a delayed response, if you will. And so that's the way to really look at hysteresis. So the device reacts, but the response to what our input signal is per se will take some time. So it's not an immediate response. It's basically reacting. And that's what they mean by hysteresis. So so with hysteresis and dealing with comparators, noise is an extremely bad thing because it can interfere with what you have going on, okay? It's a delayed effect, so you might not see it immediate, right? And that's what he's kind of relating to this here, how noise and positive feedback do what they do. Because see, the device models we've had up to this point have largely dealt with negative feedback, okay? That's in the transistor models we've had, you know, we always get the negative response or negative feedback, negative, you know, the reflections, if you will. But now we start looking at something that that's a little different, and we like positive feedback. And by saying positive feedback, it doesn't mean that, oh yeah, that's positive. So that doesn't mean it's saying that's a good thing, right? It's just the way in which it's occurring. Kind of like think of it, if you think of like the Eli the Iceman type model, it's kind of how you would have to approach this. One versus the other would be like negative feedback, and then the other would be the positive feedback would be the way to look at that. So when we look at hysteresis, the ideal way is looking at it in the inductive model, okay, where we get a phase lag response here. So they try to control that because, like in any case, I mean, positive or negative feedback does not necessarily mean a good thing, but how would we control it? Excuse me. So we look at this guy, right? We have a voltage divider model being tied in on this, the non-inverting loop in this case, okay? Now, if you remember the previous ones, we typically tied in on the negative terminal for a feedback loop. And so that was the negative feedback control. But now we're going into the non-inverting side and trying to provide a feedback loop, if you will, and leaving the inverting side wide open. And so what's one way to look at this, and hence thinking of our op-amp models, you know, if you see the type wired up this way, that's the type it would be. So in our linear responses, right, very typically our op-amp models have feedback resistor tied in on the inverting side and controlling it that way. But now if we go and flip and we go for what the non-inverting side is, now we start to go into what they call nonlinear applications. So it's a way to think of that. And a style, and one thing to keep in the back of your mind going on here is what's happening with these inputs here, right? E plus equals and follows E minus, always, always, and always. And so when we deal with that, that's how we can say, okay, negative feedback versus positive feedback. And that's what we mean by saying, oh, what the heck is this hysteresis? And so the reason we would do these type of things is we start getting into like timers with them. We can go ahead and actually set these things up and give us specific values. I mean, if you look, right, what we essentially have going in and into the voltage input in this case is a sinusoidal waveform. But you can see that coming on the output is very clear. Stop it. Is what would be considered like a square wave. And so the one thing we would have to kind of control, and you've seen that from back here, right, is how the pulse triggers. And basically we would have to consider the circuit and decide what our overall duty cycle would be. So in effect, I mean, we would have to do something further with this, because ideally, like a digital type signal usually happens from like a 0 reference point to a plus voltage, if you will, or unless we're dealing with like negative logic, but still a 0 reference to the negative logic point, right? And you can see at this one, what we have is quite clearly, because of the analogness of it all, is that we're going from the VSAT to the minus VSAT, right? So it's swinging DC wise, right, up to the top. So if we consider ideally, so that'd be like plus 15 and minus 15 going on here. So, but we could take that signal and later on and remove that DC effect and push this up and actually get an overall timing trigger if we wanted to create that. It'd be one way to look at, like, basically what, creating like an analog to a digital conversion, if you will, right? But so we could do different things with these, and then we get and these are all comparator models. It's a way to think of that. And we start looking at something called the integrator. And I don't know how much of this I'm going to give to you guys, because this is quite a lot. Now we start getting into like the more interesting effects of what the op amps are capable of, what they do with them. Basically, look at it this way: the beginning ones, right, from the previous chapter, that's all linear applications. That's like, so, and one way to say it is like, that's easy mode. Now we're going to start getting a little more into hard mode, if you will. So we can change things with this, and we have different controls depending on how we control the feedback loops. So in this case, like here, where we control the positive feedback loop and with hystereses. So he makes some statements here, and we have to look at what we're getting. Okay, so with the integrator, we're gonna start actually throwing capacitance into these guys and seeing how we can affect things with capacitance, with inductance models, and that basically will lead us up to getting into like the high pass active or low pass active filters, if you will. But yeah, these have some uses to them. Depends on what you want to do. Yeah, see in the bottom here, these will create time bases for oscilloscopes and that kind of thing. Your output ramps are almost perfect. So if you did wish to have like a triggered response, if you will, you could use this. So notice what we're putting in, right? We're putting in a square wave, and then what are we getting out is a ramp response, and that's based on our RC's time constant on the feedback loop here. And notice we are back to using the inverting input and controlling that. But our difference in this case now was we throw a capacitor in with this guy. And so our resistance value can vary, as you see here, where we get a plus or greater than or equal to a 10. So we're trying to set up some factors. And what that'll do is it'll control our ramp response, or how ideal it is. And the great thing of doing this with, compared to like doing like I say, that having these active models compared to the passive models, is the great degree of accuracy you have and the smoothness. Like you see how he says here, output ramps are almost perfect. Yeah, nothing's ever perfect, but our cutoff points at this, you have an immediate response. It's nice and smooth. You wouldn't have any like warble to it or anything like that with just like passive models. So this is a nice clean reproduction based on what our RC time constant is in this case. And that sets us up. What we start getting into is, yeah, waveform conversions and using like Schmitt triggers. Yeah, we'll start getting into some of the interesting names towards the end here too. I don't know if I'm going to go through this entire thing today because there is a lot of stuff into this. But the Schmidt trigger can convert waveforms, and it's something that, like, ideally, I mean, when you get back to it, everything in the beginning starts off as a sine wave. You know, we're dealing in the analog world. We're out here in the analog world. So the original, anything that we deal with originally starts off with a sine wave. So how do we convert it? So you get your like function generators, if you will, and they're cranking out, you know, you can get triangular waves and square waves and things like that out of them. But how do it do it? Well, the Schmidt trigger is largely involved with that. It's a very classic device model, and it's been proven time and time again. You can, and you set what they call the duty cycle of it. And everybody knows what duty cycle means, I hope, at this point, right? Is that something hopefully you've gotten out of digital, or is that something we need to address here? How we deal with like an on and off again. So basically, it's a ratio of how on you are compared to the whole cycle. Because if I had like a time period of, I don't know, a millisecond or something like that, and let's say my pulse is only on for, I don't know, a fraction of that, like, but if I say a millisecond, let's say I had it on for like 500 microseconds, right? So on would be half of the time period. So that would be a 50% duty cycle. And so basically you look at duty cycles as like how active it is compared to the whole time period. In any case, so in this particular circuit, depending, and it would depend on what type of signal we were to pump into this guy, right? Very simple. We only have what? 4 components to this guy all together, right? 2 resistors, a capacitor, and an op amp. We inject a square wave. Now this would be something where you would be getting a response out of a circuit very much like this, right? Let's say originally I started off with my sinusoidal. I cranked out the square wave pulse out of this guy, and then I fed it into a device like this, okay? And then you would have basically, and then I can convert that to a triangular wave, if you will. Why would I do that? Well, it would depend on our applications, what we're trying to go for. There's different things that'll trigger because of this. And we can even set how on we are, if you will, to how off we are. And that's when you get into things like duty cycles, where you have like a trigger pulse like this. But again, you just go back, it's really controlling how we're dealing with our feedback loops, you know, positive or negative feedback, and what we have going in and overall response. I mean, nothing is ideally perfect, but because of the op amp's abilities, like I say, this is much more preferable to like a passive style device, because we could very, very well do the same type of thing with using passive components, where we would not have that op amp involved, and we would just be using like resistors and capacitors in the network. But our overall conversion would not be as smooth, and it would not be as consistent. We do have a nice time base to this thing that's allowed, and I wish we could do, well, we might be, we can't do that with the simulator. But I wish we could do that. We could do like even a comparison, setting up similar RC time constant circuits, where you could compare like a passive filter to an active filter and see what your overall output response would be by, like, you know, comparison ratios. And I guarantee that what you get with the op amp filter compared to the passive style is a much, much cleaner, much faster, smoother signal, without the noise, without the distortion and that type of thing. So typically, I mean, when you're dealing with, especially like in audio and things like that, where you do need clean signals, this is where you would see that kind of thing versus having just passive filters. You would throw in the op amp circuits and stuff like that just to help. And we also start getting into, and see, this chapter has a lot to it. I don't know, like I said, I'm going to cover all of that today with this, because he also goes into oscillators, and then we have like a further chapter where we start talking about oscillators even more. And and what's involved with that. And there's different, oh my God, there's so many different types of oscillations out there. You get, I mean, they have like the classic, right? Sorry. Will you stop it over there? I'll get you water in a minute. Um, but we could control oscillators depending on what kind of clocking signal we're going for. And again, these guys are active generators versus passive. Because when we look in, which is weird, I don't know. In some ways, it would have helped to look at the oscillators prior to this, because they have like passive oscillators versus active oscillators. A lot of times, like in like your computer, you look at that little clock chip that you have in there, and really at the heart of that, you have a passive device where it's like a crystal that reacts to given voltage and whatnot, and produces out it gets excited, right? And what it'll do is produce a given frequency. So they literally shape these crystals to give out a specific frequency, if you will, but that would be a passive style. And then we get into this type where we are actively controlling our waveform generation. And that would be if we wanted to have like responses, we wanted to be able to have variance, if you will. Now, if you recall from like our previous 8 weeks where we had like the diode circuits with, like in this case, the half wave rectifiers, and even the full wave rectifiers, the very, very cool thing of using an op amp with that is we have a much greater degree of control with without the the distortion effects to it, if you will, and we don't have as much limitation. I'm gonna stop that with this because I'm getting into filters, and I'd like to talk about some other stuff with that too, if you will. But yeah, I'm gonna go through today, and I would really like, well, I'm gonna see if I can get a decent summing lab circuit for you guys just to be able to play with. And then ideally, we do want to do some type of comparator lab, if you will, with op amps, but I might have to go with something very simple, like along these lines. We'll basically do a zero reference lab, because anything outside of that is requiring us to go and tie in on the bias voltages for the device, which we won't be able to do with the simulator. But we can do zero reference ones where we are not tying anything into the voltage references for that. So yeah, I scrubbed lab 10. If you can, I would like you to get through labs 11 and 12 and do that. I mean, hopefully, hold on here. Oh, I'm missing out in chat. Oh, laptop's about to die. Yeah, batteries suck. Batteries suck. But yeah, hopefully, and then we can go through, and like I say, the only, if you have to control your inputs, that's basically what these are referring to, right? So your minimum, the minus side would be VEE, and then the max would be the VCC, if you will. So you would be able to control how that varies. And then think of this as, like I say, your gain factor. And watch that. See how it's that K there? So this is 100,000, which is very typical. If we did have, and that would come more from like the spec sheet, but this is the 741 model. You could say the 741, the LM741C, which is probably the most popular model out there. I'm gonna beat you. Dog's in there throwing a water bottle around. Sorry. But yeah, we can vary that, but that's typical. You probably shouldn't have to vary that through most of these labs. I mean, most of them are modeled on a 741C. The only thing we might end up changing would be like the VCC and VEE right here, if you will. And then, but yeah, I would like if you could get through, the heck was it, 11, yeah, 11 and 12 would be the inverting, non-inverting. So that way you get the overall models of the ideal op amps, if you will, just to see how controlling the feedback loops on those work and one versus the other. And that way you get those concepts in, and then we'll start playing with jumping into some non-linear applications like the comparator model and stuff like that. And really, and the thing to remember and keep in our heads here is really how we're dealing with this, when we say like the linear versus the non-linear models, and that's just how we're controlling the feedback loops to this case, closed loop function versus open loop function. So with our closed loop function, very, very typically consider that as being the linear approach to op amps, if you will. And then as our open loop functions, very, very much consider that as being our nonlinear function. And that's a case where you would have like the op amp being used as like like I say, with the active filtering or with the oscillators, if you will. So comparators, oscillators, and active filters. But they're very, very widely used for active, for most filtering is done with these guys because their response is very quick. Because the one thing, and I mean, and that's the thing with like things like hystereses and stuff, when you have like a passive filter. So let's say I set up a passive, I don't know, like a passive RLC filter, if you will. So it's waiting to respond. It's waiting to react. And in some cases, like in the case of inductance, right, you have that phase lag, if you will, and it's, lead and lag, okay, depending on if it's voltage lag or current lag, depending on if we're dealing with capacitance or inductance. But you have that lag involved always, and that response time with that involved. I mean, in the case when you would need like something where it has a quick response, you would need an active filter. In that case, you would use like the op amp filters. If you had something that was like low level signal, you didn't need like a really fast response, immediate or anything like that. Yeah, then you go with the passive filters. I mean, they're cheaper, right? But that's the main difference. So really, I mean, a way to think about that, like all your AC stuff that you dealt with basically gave you the groundwork, but all that stuff that we dealt with and that was all passive devices. They're just sitting there idle, waiting for something to happen, waiting for signals to come at them and hit them. But in this case, now we're starting to get into things that don't necessarily wait for things to come along. They're literally charged up and ready, and so by the time a signal does get there, the response time is immediate. That type of thing. Does that make sense so far? Is that kind of clear on kind of what op amps are, why we want to use them the way we do, and stuff like that? I hope. Nothing. Oh, see, this is why I wish we were in class. At least I get something out of you guys. And I get on here, I can't see nobody. All I see are like little initial abbreviations with dead microphones. And every now and then I get some class would still be silent. Not always. I had a couple of people that would always pipe up. The class, nobody wants to be the one to pipe up. Well, yeah, but so what I'm going to do today, yeah, we'll post a homework for this lab. For this chapter. But keep that in mind, and don't be afraid to get a hold of me as we start getting into this nonlinear applications of op amps. But it does set us up. We'll start getting into some classics where we'll look at what they call the Schmitt triggers. We'll end up looking at the Weinbridge oscillators. Weinbridge oscillator is extremely popular, and then there's another one that's secondary to that. We'll look at that too. But that goes into his further chapter as well, where we start looking into oscillators and whatnot. I may, depending on how this goes, we may bypass the like regulated power supplies and go and go into basically doing all the oscillations and think. Trying to remember the chapter order of this all with Frenzal. But I would like definitely for us to look at thyristors and the 555 timers involved with the oscillators would be fun, because I do know that the simulator, and that's so weird, right? So the simulator has all the pinouts I noticed for the 555 timer, but I don't have all the pinouts for the op amp model. I don't get it, but so in some cases we'll be able to do some better labs for the 555 timers than we did with the op amp device. So I'm going to try to go through these and make sure, because I have to keep it more on the simpler side. We're just dealing with feedback loops. So the comparator ones are going to be rather on the simpler side. We won't be able to do some of those just because we can't tie into VCC and VEE to create any effects, if you will. But we will be able to do some of the other ones with it, at least with the negative and the positive feedback loops, and you'll be able to see that, which will be good. And with the active filters, we'll definitely be able to set that up, and oscillators. And the oscillators, like I say, they set us up for the 555 timer. Because even though you can make some fairly decent oscillators with op amps and whatnot, eventually when they came out with the 555 timer, just your range and the ease and everything else that's with that thing, that next to the 741 is probably one of the most popular devices out there. I mean, I'm not including digital or anything, but yeah, that's what I have today. So I'll post I will post the homework for this chapter, and then like I say, we're scrubbing lab 10. I'm gonna have to, like I said, I'll come up with a non-zero model of that variation. Basically, I got a few other ones I'm looking at, and I'm just basically trying to create them. So really, the problem at this point is I had all these labs set up, and they were meant to be physically done, right? But now I gotta like convert. Well, I have to not only convert them all, I got to get everything into Blackboard too. I got to make sure that it's like working with the circuit simulator too. But that is what I have for you today, boys and girls. Do you have any questions? You guys doing all right? We're all doing okay. Is this making sense? I mean, am I spinning gears? Do I need to address anything further with op amps? Is there something that you'd like me to go over further that you're not getting? Oh my God. Okay. How did we say that from the last time? Silence means yes. Oh God. But I mean, as far as setting these circuits up with the simulator, it should go fairly decently. But yeah, I mean, no. See, I mean, I didn't change, because see, that's all part of the whole graph for it. So when you see the labs, and it's just setting that up, right? So that's telling you what the plus and minus voltage levels would be. So if it changes, like, and see, I mean, in the simulator, the classic style, it's defaulting to 15 minus and plus. So then all you have to do is worry about setting up your circuit correctly. Please stop. I mean, seriously, stop. But yeah, and that's kind of, and this is right, the non-inverting one. So the only thing you do have to go through, and like on this lab, is go through it. The 1K will stay fixed. So all you'll have to do is go through and change the values of the feedback resistor there and record them in that there table. See what your overall deal is. And I think I had the formula right there for you. So yeah, this is the non-inverting. And I mean, that's really the main difference that you'll be dealing with as far as from the inverting to the non-inverting is what your AV formula is. So the non-inverting, you always have that 1 plus R up over Ri. And then with the inverting, you have the minus R up over Ri. And so really all you have to do is take your two resistances and then, you know, just do the ratio of them and get your gain factor. And that's what that sets up. Set that up, and then what your V out would be in this case. And really that's just a 1-to-1 ratio. If I'm putting 1 volt in, right, and even looking at that, pretty much your whole gain all the way down there is because it's 4.7K over 1K, so you're gonna have 4.7 plus 1. So you go 5.7, 11, 23, 34, and 48, and which gain output based on that. But it's just getting you guys walk through it and getting used to dealing with these things right off the bat. And then, like I said, I gotta, will you please? I gotta do the zero reference comparator we'll do. And then, yeah, I gotta figure out which ones will actually work with the simulator that'll be decent for us to work with, I guess. I don't know. Oh, look, I see faces. See, some people give me faces. I don't get many faces, but no, that's what I mean, and that's really what we'll do. Yeah, definitely get through those 2 labs of the inverting and non-inverting. They're like the very basics are at the heart of the whole thing, right? To move forward. Does that make sense for you guys? Yeah. You have any questions on this? I mean, does the op amp making sense and everything? There's nothing like too crazy. It's all confusing with it as far as this goes. All right, all right, all right. Well, you know how to get a hold of me if we have any questions on this. I mean, on the plus side, we don't have as many factors to worry about, like as with transit. Where my chat thing go? Oh, good Lord. There we go. Yeah, I mean, it would be a lot cooler if we were building these in lab, right? That's the thing, because then I even had like different op amp devices. I mean, yeah, I have a bunch of 741s, but we had a couple other of the other styles. In one of the labs, we would have even gone through and you would have picked like, you know, a 741 and then 2 other op amp styles and literally kept the circuit the same and swapped them out and seen if anything changed and that kind of thing, you know. And like and doing the comparator models would have been cool too. How we can play with the input voltages like that. And that's the thing to remember with these when we apply that to it. What's at the heart here? Really don't think of them like digital input voltages, right? +5 volts and ground kind of thing, right? This BCC and BEE on those pins are still technically bias voltages, right? So we're still biasing the device and biasing the amplifier internal to it. It just, you don't see that there. But then when we go and vary those 2 voltages like that, how we can change our thresholds, right? So we change our bias, so we change what our output would be. And that's the cool thing about dealing with like a comparator. So we start getting into that non-linear response, if you will. But yeah, we'll go through. I should have, hopefully I'll have these done today. I've been working on a couple of them. And like I say, it's just a matter of getting these all converted properly and set up for the silly simulator and then getting it all into Blackboard. But I did post a quiz for the last chapter. So you'll have that to play with, and then and definitely, yeah, labs 11 and 12. Definitely get through those two, because those two, like I say, set the basis up for pretty much everything else. They're really just the basic operations of the inverting and non-inverting amplifiers. You try to change resistance values and see how the circuit responds, right? As far as like how you control your gain factor with the feedback loop. So yeah, get through those two, get through the quiz. I'll have a homework for this chapter posted, and then we'll get through that, and then we'll start getting into some cool things and making some clocks and stuff, and how we can play with frequencies. Basically, now we'll start dealing with like more AC applications of op amps, if you will. All right. No questions? Seriously? Nothing? Ah, um, Pirate. That's enough. Yeah. Yeah, I'll see. We'll see you Monday. You guys have a great, well, nice rainy, gloomy day today, but try to have a nice weekend. I know, right? This spring has really been bumming me out. It's been cold and everything else. I'm like, oh, I'm ready for, well, we had that, what, those couple of days were pretty nice, and that was all ready for all that. I want some more of that, but I guess we'll have to get what we get. But his silence goes to show how confident we are. You know, you're that confident. All right, all right. Well, when we come up on that final, we'll see how that confidence comes through there, Mr. Cargill. And in some ways, I almost want to even do like I'll give you a lab final. We haven't done that yet, and we'll do something like crazy with some kind of op amp oscillator or some kind. It'll be like, all right, if I want to have a clock frequency of this, and then you have this, tell me how you would do it. Oh, not that much confidence? Okay. Oh, we'll get there. Actually, I mean, that would be one of the things we'll come out of there with, right? You actually be able to set up, being able to even set these up, and even doing, if you needed to, you could even set up like your own little power supply, if you will. How we can convert like a nice AC signal into some kind of DC and stuff like that. You know, get you a little dangerous. But yeah, we could. And that is one. I mean, we'd be using the big can op amps, but we could totally. We'll look at the regulated power supplies. That's a cool thing about using these. You have like the active ones, right? So we can actually. I mean, you've seen those op amps can go from what 3 to 10 amps. So we could set up a nice little power supply, even inverters and stuff like that. But yeah, these guys are always at the heart of all of that. And then we basically, the cool thing is use all three of those things at that point: op amps, transistors, and diodes, right? Just for different purposes. Thing with diodes, it's like usually they're nice little blockers. A lot of times that's what we do with them, right? Keep unwanted signals out. So if you see like a diode being tied to ground or something like that, yeah, what's his purpose? It's like, yeah, he's blocking, clippers, blockers, setting up little voltage thresholds. Diodes are pretty simple in that effect, but they're nice to use for that. Or in a case like the Zeners, right, where we're going for voltage references. And you'll find those used. See, the one drawback with using a Zener is that you can get the voltage, you just don't have no kick for it. So you don't have no current involved. So a lot of times what you'll see though is on like on DC power supplies. And in fact, this is such a crazy way to save some money, right? A lot of these DC power supplies in these warehouses and factories go bad. And the reason being is that they'll have a Zener in there kicking out, let's say you got a 5-volt power supply, a DC power supply being used somewhere in the plant, right? So it got overloaded. Now it doesn't kick out anymore. Well, the funniest thing is it usually will work but that they use a Zener as a reference. So what it looks for, it's like a safety check. So it compares the 5 volts to the 5 volts. So the power supply is generating 5 volts, but it has current, right? So that's a nice kick to it. And then you use a Zener as a reference to compare is my 5 volts really 5 volts? So what would happen is the power supply looks at what the Zener has, and it does with the comparator circuit. And if all things created equal, if they both balance out, boom, I get my output. But if the Zener gets popped and goes bad, and let's say the Zener is now kicking out, I don't know, some weird voltage or even a 0, if you will, when it goes into that comparator, what it's going to get out is craziness. And so it literally stops the whole power supply from working. And 9 times out of 10, that's what's your problem. You go in there and change out this little 20-cent Zener diode on these power supplies, and ta-da, turn around and sell it back to them for like $500. No, I'm serious. So you get a lot of these. You get those ones on like eBay and stuff like that, and you'll even see it advertised. It says, "No output, unsure what's wrong." And 2 things. 1, go through and change all the electrolytic caps on that damn thing. And 2, change, and you'll see it on there too. Usually they have it, and it's a little jelly bean part, right? It's a little Zener in a little plastic case. So you just go up there and look on the front somewhere, usually right by where you're tuning, where you have to adjust the voltage level for the power supply. Usually right around there, there'll be like a little a diode model, a 3-legged model on that. But you go and change that bad boy out, and I can promise you, and along with the electrolytics, yeah, you could change that. You could change that power supply around, and that's a way if you ever really wanted to get like a power supply for cheaper. Look on eBay and find one that not working, and yeah, go through there and change out that Zener reference and change out the electrolytic caps, and you got something that'll that you just basically, some of those ones, like the heavy industrial ones, can be damn near like $750 for, if you want the ones with the real like current boost to them. They're gonna be quite expensive. I mean, I don't know, depending on what you want to do with it or something like that. Or anyway. But all right, gentlemen, boys and girls, moms and dads, children of all ages, that is. Good God. One of these days, I'm going to get better at this controlling here.
We have power supplies at work that fail in our elevators all the time.
Yeah?
Yeah, in our car top junction box, and the 12-volt power supply drives the LEDs, and they go bad all the time.
Yeah, I used to get them. We used to get these. I can't remember the SOLAs. I think were done by Emerson Electric, and they were bought out by Schneider, I think. But yeah, we used to get those in. They're really popular, rack mounted ones, because they go in all the getting your DC and your PLC racks and whatnot. Yeah, those would go bad all the time, and yeah, I swear to God, usually it was that reference voltage went bad, or one of the electrolytics.
These are little tiny. The ones I'm talking about are little tiny DIN rail mount ones.
Yeah. Probably only crank out about maybe an amp most.
Yeah, super low amperage. It's just turn on some LEDs in the car of the elevator. So
yeah. What do the new ones go for? Something like that, about $300 somewhere around.
Well, these are like really cheap. I don't know if you've heard of the brand, but they're Delta power supplies.
Actually, I have seen them. Yeah,
I think they're only like $85.
Oh.
And I don't know if they're I don't know what their class is. Power supplies are rated by class.
Right.
Yeah, I don't know. I can't remember what they are, but yeah, they go bad all the time.
Oh yeah, well, and because like $85, right? They're using little jelly bean cheesy parts.
Yeah.
The reason I call them jelly beans, it's something we used to call back in the day. It's like it's one of those deals. You get a big jar of jelly beans, just reach in, and besides the colors, it's like okay, it doesn't really matter, right?
Yeah.
they're cheap, and there's a bunch of them. But yeah, yeah, because we used to be able to change those out all the time, changing out caps and stuff like that, and how much they charge for a pair on those is just nuts. But yeah, if it's $85, it's almost not even worth.
Yeah, we don't even get them back. We just send them out new ones if it's still in warranty.
Yeah.
Because I think our in order to get something back, it has to be over a certain price, and it's like $180, or else it's not really worth it.
Yeah, I wouldn't be surprised. I'll tell you honestly, I bet you 50 the reference voltage on those things is what's going bad on them.
Yeah.
Because we'll look into it a little bit. We got Frenzel does a whole chapter on regulated power supplies, and you do get I mean, there's some fairly simple. It's they're usually not that complicated. The biggest, or most of them, you always see that transformer on there, and that's the one that's usually taking up the most room on these devices because you just can't limit the size of a coil with a big iron rail to it, right? It's like, no, we can't deplete the size on that. But yeah, they got I mean, you got your input where you got a bunch of, and this is how you can always tell if you're dealing with something really good or not. Look at your input on those power supplies. If you see a fair degree of components to it, where it's getting the AC in to the fuse, then you got a pretty decent one. If you see it where it looks really simple, like there's only maybe one or two capacitors and a couple of, like a diode and a couple of resistors, yeah, that thing's cheesy as hell. Because you want the filtering in the very beginning, because you want to, when you're converting your signal, it puts the least amount of stress on your other stuff, right? So the real expensive power supplies, yeah, that whole input deal is usually packed because they want to make sure that the signal they're getting in is super clean, not going to short anything out. Especially the industrial ones, where you're more susceptible to getting like crap ground bounce and all that. Because we used to get, I don't know, these one machines, especially when you send stuff to Asia, oh my God.
Yeah.
Their power there is so irregular, but they had a thing, we had our machines and they were hooked up to their power out there and they kept getting these glitches in them, but only in Asia. And then come to find out that, yeah, every time, because the way their ground was, they do like a all delta out there. They never do any Y configuration. So whenever you would power one machine off somewhere down the line, powering it off would make enough ground bounce to interfere with our other machine. So yeah, we had to start sending those things out with noise filters on the inputs. Like these big honking iron ferrite beads, basically, coil thing. But yeah, man, it was our Asian rework, we called it, because of their horrible power out there. I don't know. We take a lot of things for granted. I'll tell you what, our power compared to, well, besides Europe, anywhere else in the world, it's so awesome. You start getting into these other areas and stuff, and oh my God, and you got to think of that. That's why a lot of these like power supplies are built like that. They have to be, because you're not just coming to the United States and Europe. A lot of times these days you're going, somewhere else for manufacturing. So they beef them up. But yeah, that's how you could tell. It's basically the input. Now what kind of little transformer you got on that thing, and that kind of deal. And yeah, usually it fails on those. Is the reference voltage, believe it or not. I used to fix quite a few of those. I mean, they're a pain in the ass, but I don't know. You could always refurbish a power supply, get it going again. But yeah, we'll look at them. I mean, a fairly simpler approach. We won't be doing like anything ready for industrial models, but you get the idea of how they work. And the flyback, always fun. And that's where, getting into this like closed loop and open loop, getting that into your head and like how this is working. And then that'll help us a lot when we go into regulated power supplies too. That'll be fun. But yeah, all right. Well, so you doing okay with everything, Sam? You got that Q point stuff going down
Yep.
over there? Okay.
Yep. Yeah,
Yeah,
it's making more sense. It's making more sense now for sure. And op amps are even easier than transistor models.
yeah,
So
and really they are. Once as long as we don't get into anything too crazy, it's everything's happening internally now, so we don't have to worry about it, right?
yeah,
Our biggest thing is, like I say, setting our values for the resistances. Well, we are going to look at some of the crazy stuff coming up here with starting to throw capacitors and inductors in there for our feedback, making these oscillators. But that's
yeah. Are we
about.
gonna do like crystal oscillators and
Now
or
we
we'll
are going to look
like,
at those, but he does that. He actually has a whole chapter 39, I think. Yeah, I think I'd have to look again, but I think chapter 39 is all about oscillators and frequency synthesizers.
mhm.
So yeah, we'll look at crystals, which sucks too, because I got a whole bunch of crystals, which we're not going to really be able to do, but we'll look at the active oscillators for sure. But yeah, we were going to look at with crystals and generating those out, seeing how that works, and then doing like some active oscillators, basically generating clock functions out and this kind of.
Yeah, it's cool.
It is kind of cool, because you can do a lot of stuff with those depending on what
Oh
you want.
yeah. I've been getting into like video synthesis, analog video synthesis,
Okay.
because you can just make crazy shapes and patterns with different ramps
Oh
and
yeah, and and then yeah,
sync. You know,
so getting into what we're starting to get into, you'll like that more with the op amp models, how they're, like I say, with that, like even looking at that ramp function with that,
yeah.
kind of what they're, yeah, there's a lot of it sets up
I could
for.
yeah, that's what I recognized it from when you were going over it today.
Yeah, because they consider that, because yeah, all this open loop function stuff, that's a lot of audio is involved with that, audio or even the video signals.
Hmm.
I mean, the one thing we don't get into later on, we won't be getting into, and that's a further electronics thing where you get into like the modulation and demodulation.
Yeah, frequency modulation.
Yeah, yeah, that's a little bit past what our scope here. That'd be if you really wanted to go for more of an electronics type degree, but yeah, you start getting into modulation and demodulation, and then yeah, now you're starting to get the whole full. And there's so many types, frequency, pulse width modulation,
Hmm.
even the old school, well, the original, right? AM amplitude modulation, see how,
Hmm.
how that works. But yeah, there was a lot that went into that, and the demodulation circuits too. But yeah, we don't quite get in that far, but but we'll get
Yeah,
into
that's more personal interest anyway than
yeah, it's the
career
obvious type
wise.
of thing.
Yeah,
Yep,
yeah.
yep. No, that's pretty cool. Well, and it would be a thing, this will give you enough some good building blocks, and then you can head on for your own personal interest, and then
Yeah, really, it already has. I mean, there's a classic fuzz and distortion pedal that I'm building from a schematic that I found actually, and it's cascaded stages of gain
okay.
with I'm looking at it here with some capacitors and potentiometers for different stages of gain.
Oh yeah, so you'd be able to set what your references are and everything.
Yeah,
Right,
yeah.
right. I didn't even think about that. Yeah, a friend of mine used to play guitar in high school heavily. He had like the wah wah pedals and the distortion
Hmm.
pedals, right? Wah, wah,
I
wah.
just thought I thought it was cool, and all the parts were like really cheap. Like I just ordered a ceramic capacitor kit from DigiKey, and that was like $30 for thousands of them.
Yeah, it's crazy. Well, and that's yeah, you buy in
And I got some op amps and transistors too.
now were you using that finechips.com for that or just on.
Yeah, I did use Fine Chips, and then it sourced the best. It said the best deal was at DigiKey, so that's the one that I got.
Yeah, I love that and a lot of
It is
people
cool.
don't know what's out there. And I was like, oh hell yes, look at this. And then you can even find like the data sheets on stuff with it and everything else.
Yeah,
Nice.
yeah.
So
I've been using it a lot.
oh no, it was like one of my main it's been around a while, believe it or not. It was one of my main tools. I had like or two other ones. One was kind of like an old, trying to outsource like old devices kind of thing, looking,
Hmm.
which is always a pain. But you won't hopefully have to deal with that. But yeah, I like that because it looks like I say a Mouser, Alliance, and DigiKey and
Yeah.
all of them.
And it sucks not having like a Radio Shack where I could just go and buy all of this stuff that
You
I
know,
want, you know?
we could walk in and well, when we were able to do it, the guy would literally give you like a little brown paper bag, right? And they had all these drawers. So you go up and it's like, okay,
Candy
so
store style.
oh yeah, so you go up, here's your capacitor section, you see the values all laid out, open these drawers up, and yeah, it's all just laid out in like these little bins and stuff. So you grab as many as you need, and you can even like the hardware store. So you take these little bags and you start right on there with all the stuff was.
Yeah.
But yeah, they started, I don't know, more and more you'd walk in and literally go in and a lot of those bins would just be empty. They weren't stocking them anymore and crap. And like we were saying earlier, it was just they were selling toys like cell phones and RC
Yeah.
cars and crap.
I
But
know it's kind of weird because there are still electronics enthusiasts and hobbyists out there, so but they're not really served with a brick and mortar store anymore.
oh no,
It's a shame.
well, and then trying to order, like even trying to order stuff from DigiKey, as a hobbyist, you're not looking into, I need 100 of these. It's like no, I need like one to five.
Yeah, I know. Yeah, you get a price break for every 1,500 that you order.
Right.
Well, I don't have, you know, $100 to spend on this stuff.
Oh no, when I was at work, that would work out great because then it would be like, okay, well, how many do you think? But then you had to do a whole perspective on it too, right? I'd have to literally draw a paper up for the buyer, like, okay, how many of these repairs do you think we'll be getting in? So how many of these devices will we need? Do we need to make a
Yeah,
spin for it? Because we used to keep, more of the commonly used stuff. I mean, we had limited space, but we did keep a wide variety of like the common electrolytics, resistors, and all that kind of crap. It was just when you ran into oddball ones, it's like, oh, do you think we're gonna do enough of these where we need a part spot for it, or just order them as we need them?
yeah,
Because
that's
yeah,
kind of what
usually,
I'm. That's kind of what I'm doing. I'll show this really messy workbench. You can see that, but I have one of those.
oh yeah, see, yep.
I'm kind of just filling it up with stock components that go in everything.
Now
So
we used to have at the one place I worked at, we had like that where you had those little plastic things, but it was on a roll around, literally
Mhm.
from like about 6 foot up, and yeah, you would spin it around, and that's what we had all our resistors on, and then we had another one similar to that, and it had all like the capacitors, like all the electrolytics,
Yeah.
and then we had weird spots where yeah, we kept the chips and like Mylar caps that weren't as commonly used and stuff like that. But oh my God. Yeah, it was kind of fun. I got one of my major skills. I'm a killer with a soldering iron.
Yeah. I'm
Oh,
getting I'm
yeah,
getting there. I have to solder a lot at work though. For some reason we buy these boards from Porta and they already have everything soldered onto them. And
how do you use are you
I
using
use a Weller. I
electric?
have a Weller station.
Okay, I was gonna say because I had one place I worked at, we were doing weird stuff, but I had one of those propane soldering irons.
Oh yeah, my stepdad has one of those. It's pretty
And
cool.
they actually amazingly work for and you're limited, right? But it for being able to touch up stuff and everything when you're up on a ladder or something like that.
Yeah, it makes like heat shrinking tubes way
Uh-huh.
easier.
Yep.
Those are really cool.
I even had
That's
to
a
touch.
little out of my league, but
Oh, well, yeah, no, I got pretty good with soldering. I even do like, well, I was telling you before, but like doing surface mount, which a lot of people are scared of. But
like in a soldering pot or wave solder.
oh no, I can hand solder surface mount.
Nice. I can't do that.
Well, it's a trick. But you need more than one soldering iron. But
Oh. Hmm.
yeah, so if you got, because so like surface mounts usually like on a square pad, right?
Mm-hmm.
They got the four sides to it. Well, all right. So here's your trick. So you get low melt, what they call low melt solder. It has like a lower melting point than your traditional stuff.
Mm-hmm.
Okay. So you take the low melt solder, so that way it heats up fast and you can spread it around and keep it heated. So you get all your 4 points, like all your 4 sides, get them all heated up. And then what you do is you take your 2 different soldering irons and you have to alternate a bit, but you keep holding them like from each side to each side. So on one point you'll have like, doing 2 and hold
Mhm.
it there and hold it there and then switch and hold it there and hold it there. And little by little, and all you got to do is like a slight wiggle test to it, and you'll see when the whole pads start to lift up, and don't force it, just real nudge, because it'll slide right off, and then once it literally slides off, you pull it up, and then what I used to do was use solder wick at all, like the copper braid stuff.
I don't really have to. Usually, I have a soldering pump.
Okay, well, this is when solder wick becomes really nice. So what you do is now you have the bare pads open up on your PCB, right? So you I used to get a nice, not a real wide one, but a fairly nice flat copper braid, solder wick.
Hmm.
And I would lay it across there and literally just with my soldering iron just touch up and remove all the low melt solder and any of the other solder that was left on the pads, and it'd be all nice and clean.
Yeah, that's cool.
Oh yeah, you can totally do it. There's tricks, and then I'd have to show you how to reapply it. But I had this rework girl one time, and she was amazing, and she showed me how to do this stuff. But I was like, all right, how in the hell do you solder these pads all down without getting it all like buttered up all over the place? Where you got the big globs.
Yeah.
And I swear to God, it was like magic watching her. I was like, I'll be damned. And ever since then, I've actually had real good luck with it too. I've never had a pad that wasn't soldered down or anything. And I've even had one guy, he goes, "You soldered this on here?" And I was like, "Yeah." He goes, "Wow." He goes, "That's like so professional." And I went, "Yeah."
Yeah, I thought the only way you could do surface mount was with wave solder.
Nope. I do it with 2 Wellers.
That's awesome.
I swear to God, 2 Wellers and solder wick and yeah, a thing of low melt solder. I swear to God, and yeah, you wouldn't. I mean, we had, I had the rework stations where, yeah, you had the square pads for the different SMT styles and stuff, right? And they even had the hot air flow to them and whatnot. Those things
Hmm.
suck. They suck. I would much rather, like I say, do it with the 2 Wellers and go at it the way. Yeah, if I would, if we were in the lab, I'd be able to show you how to do it, but.
You're right.
But yep. No, I used to do a lot of rework and stuff, but not anymore. But just home hobbyist stuff now. Oh, am I still sharing? Oh, my screen sharing is paused. Well, that's good. We're not sharing. There we go. All right. Well, I guess I will. Well, yeah. What is Wednesday today? So I'll see you guys next week. But yeah, I'll post some stuff up. Hopefully it works well with the simulator, and then but yeah, go through those 11 and 12 just to do the inverting and non-inverting and get
Yep.
that down, and then I hope I can get the zero reference comparator down, because that's when we start getting into the ideal non-linear applications comparator.
Yeah, interesting stuff.
Yeah, it'll be kind of cool, hopefully, and then yeah, we'll start getting into oscillators. It'll be more
Yeah.
fun. All right, buddy. Well, good luck. I'll see you. Yeah, I'll see you.
Yeah, I'll see you next week, Tom. Thank you.
You're welcome.
Yeah, see you, man.